Perfect. Okay, so thank you. I see the slides are coming up. We'll get started in a second here. I do want to welcome everyone again. This is going to be, it's been an exciting day. I keep mentioning you're all a part of history with the rollout of the first Earth shot, hydrogen energy Earth shot. Earth shot today. This is exciting for all of us. So it's really fitting that we were ending the technical sessions today on this integrated energy systems, coming back to the collaborative nature of hydrogen across all of DOE. So again, I think we can get, I think I'll start with introductory remarks. I'll have all the panelists introduce themselves and their great work and their leadership in this space when they get the mic. But before doing so, I want to provide a couple of background pieces of information and some context to this panel. So I see we've got the H2 at scale bubble chart up, and I'll spend a few minutes on that. I first want to start out by saying that diversification and hybridization of energy systems in the United States and across the world is happening, and it's inevitable. It's inevitable and it's necessary as we strive to meet growing energy demands while also trying to, or not trying, while also achieving decarbonization and addressing climate change, as at the same time addressing environmental justice according to all of the administration priorities. So, it's happening and it's going to happen. And how does it happen is really depends on the experts that know what they're doing and how to pull it all together. As we've been hearing all morning, the H2 at scale, which is a really good illustration in what's now the famous bubble chart being shown on your screen, really embodies many of the key features of an integrated hybrid energy system, where in this case, affordable clean hydrogen really opens a lot of new integration pathways that complement both the electric power grid as well as the natural gas grid infrastructure. And by doing so, this really can help enable a clean energy future. So that's kind of what, the overall overarching motivation between H2 at scale is this flexibility offered by hydrogen as a new component of the energy sector. If we can go to the next slide, please. Thank you. As Sunita showed in her plenary session, and as Jesse described, there's H2 at scale projects are currently underway in communities across the country that are demonstrating some of these interesting and exciting opportunities to integrate diverse energy resources with multiple end uses. Again, leveraging hydrogen as a primary vector for clean energy storage, transport, and utilization in all of these spaces. Now, I won't go through all of them again, but I think a key point is that the flexibility, the interesting thing, and whether that's from nuclear power, from renewable resources, fossil energy resources with CCS, being able to couple these together to meeting the end uses, not only in the power sector, but also transportation, chemicals, industry, all of the things you've been hearing about in the previous talks. I think that really opens up a lot of new opportunities, not only for creating economic growth, but also decarbonizing the energy sector, which is a really key priority. Now, one of the other things I want to emphasize in this particular slide is that it's not, now that we're hearing about the hydrogen Earthshot, which we're really, really excited about, certainly a key requirement is going to be the availability of affordable clean hydrogen at large scales. But keep in mind, we really also need to develop a new workforce to take the lead in these new technologies. So that's a big part of this as well. If we can go to the next slide. I just want to take an opportunity to emphasize how high the stakes are for our clean energy future. It's an imperative. And the hybridization and integrated energy systems in the energy generation, storage, transportation, utilization space that we'll be talking about today, they're going to play a key role in this clean energy future. And so with that in mind, we are extremely fortunate to welcome experts from across DOE to discuss not only the opportunities, but some of the challenges that we can address collaboratively in this hybrid and integrated energy system space, specifically looking at what hydrogen could do to help this along. So let's start out with Eric Shea, who's been up since 2 o'clock in the morning, doing international talks across the board. Eric, if we can move to the next slide, please. And Eric, if you can take the reins, we really appreciate your joining us today. Hopefully we can keep you awake through the rest of the session. But I think it's exciting enough and it'll keep us all awake. We really welcome you here to give us an overview of the Energy Storage Grand Challenge that's been a key part of past years in the department that really have led to some of the innovations in integrated and hybrid energy systems. So Eric, if you can take it away.
Great, thank you, Eric. And the feeling is mutual. I hope I keep you guys awake as well. If we can go to the next slide. So as Eric mentioned, I'm wearing two hats today. I am from the Office of Electricity, which handles R&D for all of the stuff in between. So all the connections from the meter to the generator, step-up transformer. So if you can click 3 times, there's a couple things I want to highlight from the Office of Electricity's portfolio. The first is, of course, the energy storage program. Now while what OE works on is more grid-scale batteries, you did just hear Neha mention that we co-sponsored a study on valuation, and that's within our regulatory environment section within OE's storage program. And really, once you get past the revenue meter on the storage resource side, the valuation issues become largely technology independent, and we're very fortunate and happy to partner with other offices like hydrogen to look at cross-cutting issues like market access, regulatory issues, and valuation. I'll also highlight the Transformer Resilience and Advanced Components program, which looks at power electronics, one of the key components for interconnecting newer resources to the grid. And then the last thing I'll highlight is the microgrids program within the Office of Electricity. So generically, when you think of close coupling of resources, especially with the way that hydrogen can be co-produced and be operating in conjunction with optimizing the way it interacts with the grids, the kinds of generic algorithms and controls that we're developing in the microgrids program can be largely applicable to many other resources as well. Next slide, please. The other hat that I'm bringing to this presentation is as one of the track leads for the Energy Storage Grand Challenge, which was started last year by DOE and really leverages later stage commonalities across the department. So very similar to what I just described in terms of co-sponsoring later stage work with a specific office, the ESGC is systematizing opportunities for DOE and the industry as a whole to accelerate cross-cutting initiatives later on in the technology maturation scale. So if you look at the scale from materials to devices, all the way out to investment operations and value, again, as you move later on and into greater stages of integration and grid operations, the ESGC will leverage those commonalities to accelerate integration, deployment, and commercialization for all technologies, including bidirectional, electrical, chemical, and thermal, where hydrogen would fit, and flexible generation and controllable loads, which is another area where certain applications of hydrogen can also fit. Next slide, please. The way we're doing that is a little bit novel for DOE, or at least at the time that we created this, which is we started at the end and we identified a set of use cases for how storage could benefit a diverse selection of end users. And so there's facilitating grid decarbonization, I'll highlight there, as a very large use case for the grid, as well as electrified mobility. You've heard descriptions of that already today, as well as facility flexibility and efficiency. And again, operationally with close coupled systems, that's one of the other use cases that would be of relevance to this group. Next slide, please. And then the way we link these use cases back to R&D strategy is to show, to draw a very clear line from the foundational R&D work in materials or algorithms through products to the use cases. So we want to have a very direct line of sight from early stage research to how the technology will ultimately be used. And it's with that hope that we anticipate that this structure will help us accelerate R&D to commercialization. So with that, I'll hand it back to Eric, and thank you very much for inviting me to the panel.
Well, thanks, Eric, and please stick around. We'll be back to you shortly. All right, so can you go to the next slide, please? All right, and I do want to highlight that as a result of the past year's work in the energy storage, that the whole DOE came together to publish a really important online report that I encourage everyone to download. In the meantime, that spurred a hybrid, and what we called it, a task force. We had an internal task force that really was born out of those efforts to really look at the opportunities for hybridization of integrated energy systems. One of the leads on that task force is Paul Spitzen, who will now talk to you about a publication that came out of that important activity. Paul.
Awesome, thanks, Eric. So my name is Paul Spitzen. I work in ERE Strategic Analysis Office. We predominantly focus on ways to optimally integrate different ERE technologies into the broader energy system. So obviously, hybrids are a great example of that. So as Eric mentioned, about a year ago, DOE kind of organically formed this hybrid energy task force. We came together and had three major questions. So you want to go to the next slide. So the first question was, how do you define a hybrid or integrated energy system? Then what are the biggest research and analysis questions that are still kind of out there? And then are there key areas where different DOE offices could coordinate or collaborate on for future research? So after assembling, folks from, ERE, NE, FE, Office of Electricity, the whole National Lab complex, we realized, one, that there's a ton of existing work across the complex on hybrid energy systems. And also, there's still a lot of work left to be done. So going to the actual report, one of the first steps we took was trying to think about what's the scope of a hybrid energy system. And so the way that, the organization parameters that we built were, first, it has to be comprised of at least 2 generation storage or conversion technologies. Second, it has to have some sort of overarching control structure, but it could be, co-located with, essentially separate subsystems. It could be virtually connected, or it could be kind of fully integrated, both virtually and physically. Also, that there's kind of a wide range of applications for these hybrid energy systems. So they could be in front of the meter, they could be behind the meter, they could be part of a microgrid, or they could be in off-grid applications. And in the last piece is that there's also a variety of products from a hybrid energy system. So it could be, anything from electricity to heat to hydrogen to syn fuels to oxygen, the full spectrum of potential outputs. But what the ultimate objective is that in order to truly be a hybrid and be of value, you have to achieve some sort of cost savings or performance improvement relative to the standalone systems. Otherwise, there's no point in even combining these things together. And so with that, I also want to highlight that there's a number of existing DOE hybrid projects. So you have flex power in ERE, you have CSPs plus thermal energy technology in the solar office, use nuclear renewable hybrid energy system plus low and high temperature electrolyzers. That's both ERE and nuclear office. There's also hybridizing existing thermal generators in the fossil energy office. And so if you go to the next slide, the report essentially targeted 3 areas for future collaboration on hybrid research. So the first area is going to be in this markets and policy and regulatory space. It's for some really simple things is that, we need to understand where the markets are today and where they're going in the future in order to optimally design hybrid systems. And then also we need to think about how these systems are going to be integrated into the existing planning processes. So, how are they going to be interconnected? What's their impact on transmission, things like that. On the valuation side, obviously, you're only going to build systems that provide value. So one, we need to figure out, how do you measure value? What services can these systems provide? Do they have complementary characteristics? What are the different cost synergies? Sources of value. So again, what markets they can participate in, what products can they offer? And then lastly is, how can you estimate the value? So thinking, plant versus, grid optimization, are there retrofit opportunities? Can they be used to mitigate forecasting errors or improve resilience? And then lastly, on the technology development side, we thought of, how do we figure out what the next level of controls, development and testing are? What are the facilities that we need to do that? How do we think about plant level design and optimization? Where are the areas for component testing, especially for things that might be synergistic across multiple technology platforms? Can we identify key demonstration projects that might benefit multiple DOE offices? And the last pair is obviously the enhanced conversion strategy. So thinking about, as part of a broader energy system, how do we meet our climate goals, and how do we imagine future conversion processes in order to get there? And so with that, I hope that you all can download the hybrid opportunity report. And again, we look forward to continued collaboration across DOE on hybrid energy systems.
Great, thanks, Paul. If we go to the next slide. As luck would have it, we have DOE leadership and 4 of the case studies that Paul just described. So with that in mind, let's first introduce Jian Fu from the Wind Energy Technologies Office, who will talk to us about some of the opportunities with wind specifically, and a little bit about the Flex Power project. Thanks, Jian.
Thanks, Eric, for the introduction. Good afternoon, everyone. This is Jian from Wind Office. In Wind Office, we have, next page, please. Yeah, in Wind Office, we have 5 programs to address R&D challenges for 3 wind types: land-based wind, offshore wind, and distributed wind. U.S. wind resource is vast, and it is expected to play a major role to achieve the administration's decarbonization goal. Accelerating wind deployment requires R&D investment to aggressively reduce costs, to advance in manufacturing, supply chain, and workforce, to address siting and market barriers, and to resolving grid and transmission with storage and other technologies. For the system integration program that I lead, the program goal is to fund R&D that ensure large amount of wind can be connected to the transmission grid. We also want to ensure a system with high amount of wind can be reliably operated. Grid services can be provided by wind and hybrid wind systems. We also want to make sure that further reduce cost and enhance performance of wind power electronics and the associated balance of the plant. A lot of system operational challenges with large amount of wind are associated with the wind energy's variability and uncertainty. There are many different approaches to address it, such as improving wind forecast, increasing system flexibility by responsive load, and deploying grid-tied battery systems. We understand that wind and energy storage coupling together can not only smooth out the variability, reduce uncertainty, but share the transmission infrastructure and reduce wind curtailment. These are the main drivers when we started funding a wind hybrid project. Next page, please. Flex Power is an ongoing project looking into wind hybrid with a wide range of technologies. It is a GMLC project jointly funded by Wind Office, Hydrogen Fuel Cell Technology Office, Water Office, and Office of Electricity. This graphics shows all components that will be part of the Flex Power hybrid plant. This hybrid plant has a combination of several renewable generations, wind, PV, and hydropower. It also has a wide range of storage technologies with various temporal characteristics to offset the variability and uncertainty of renewable power. This includes a fast responsive ultracapacity and flywheels, lithium-ion battery and flow battery, pumped hydro storage, and the hydrogen fuel cell as long duration storage. Flex Power project now is halfway through. It has almost completed the characterization of each component and is developing plant level optimization controls that enable full dispatchability of hybrid plant. The demonstration will happen later this year and earlier next year at NREL's Flatirons campus to leverage the existing mega scale physical assets and upcoming new facilities, including CGI #2 and future mega scale hydrogen facilities. In Flex Power, we model the full cycle of hydrogen from electrolysis process to fuel cell for electricity generation. Right now, the project team is establishing high-speed data link to connect 2 more remote hydrogen facilities, one at NREL ESIF and the other at Idaho National Lab, for those facilities to participate in the hardware in a loop demonstration. For Wind Office, offshore wind is uniquely positioned to produce hydrogen through water splitting electrolysis, especially when clean hydrogen can be produced cost effectively using otherwise curtailed offshore wind. Hydrogen has other uses other than electricity, such as to produce renewable fuels. When and how much offshore wind electricity should be used to generate hydrogen are dependent on many factors, including wholesale electricity market price and commodity market price. Flex Power is considering those factors in designing the optimal controls. There are many future opportunities to work R&Ds on working offshore wind and hydrogen facilities. We are looking forward for these future opportunities. Back to you, Eric.
Perfect, thanks, Jan. Great. And let's move to the next slide. And while we're on the renewable utilization theme, we'll look at solar energy. And I think one of the areas that is emerging of importance that maybe is underlooked often is thermal integration. I think we'll see this definitely in the solar space, and we'll come back to it, I believe, in the nuclear space. But with that, I'd like to introduce Avi Schultz, the program manager for concentrated solar power at the Solar Energy Technologies Office. So Avi, if you can take it away.
Great, thanks, Eric, for the introduction, and thanks everyone for having me here. So if you go to the next slide, so as Eric said, I'm the program manager for concentrating solar thermal power, or CSP, which is, I think I'm on this panel because CSP is inherently something of a hybrid technology. By decoupling collection of solar energy through a solar field of mirrors, heating up some fluid that is then readily stored through thermal energy storage that can then be dispatched on demand. So what CSP really is a source of solar thermal energy, so renewable thermal energy that can be delivered to either an industrial process, a chemical process, or most typically, to date at least, a turbine to generate electricity as needed, really 24 hours a day. And there are CSP plants out there that have been built with even up to 17 hours of thermal energy storage that are commercially deployed today that can essentially deliver electricity 24 hours a day. There are two flavors, I'll say, of commercial CSP technology that are currently commercially available, delivering heat at either 400 degrees Celsius or more recent tower configurations like the cartoon that's shown up here are operating at about 565 degrees Celsius. We're currently in our program working on research to even push the temperature of these systems up even higher, up to above 700 degrees Celsius, both to improve the efficiency of the power production side of the CSP plant, as well as to increase the flexibility of the range of industrial and chemical processes that CSP can deliver heat to. So all of what I just described means that the design of a CSP plant is intrinsically an exercise in hybridization. How do you want to use the thermal energy? How do you want to use the electric energy? And what processes are you delivering that heat or electricity to? Next slide, please. One thing we've been really thinking about in our program heavily recently is not just how do we store energy on that daily diurnal cycle to manage dispatchable electricity kind of in the daily peaks, but how do we use the thermal energy that we're collecting in a CSP plant to store renewable energy, solar thermal energy, at very long durations to really be able to affect seasonal mismatches between renewable energy resources and the energy needs. And really what that means, you know, and of course the reason I'm here at the hydrogen AMR is because you really likely need to do that in the form of chemical bonds. Whether that's hydrogen or other chemical bonds is something that we're looking into in both options. But what that means, kind of shown on this diagram, is you can have your direct thermal energy storage system where you say, you know, typically have tanks of molten salt, and you can have, as part of that plant and in varying, you know, configurations and sizings thereof, you can have an indirect thermal energy storage system where you're using that heat to directly produce hydrogen or other chemical systems. And I'm just showing on the right side of this slide just a couple of examples of projects that we currently have looking at different ways to do this. So for example, Arizona State University is looking at actually designing a CSP plant with multiple different tiers of duration of thermal energy storage, both conventional tanks, molten salt tanks, a high energy density metal oxide based thermochemical system, as well as using that thermal energy to produce hydrogen directly for very long duration storage. You can also imagine systems like what I show here that Michigan State University is working on, where you can actually think about alternative kinds of long duration, long lived chemical fuels here based on a metal oxide based system that is thermodynamically reversible and a solid fuel that's readily stored. You can also think about variations of that metal oxide system, and we're looking at this in our program, where that metal oxide isn't just something that you can cycle back and forth, but could actually be catalytically active, again, for hydrogen production. And that's something that we think is really interesting, again, intrinsically incorporating the thermal energy storage into the solid catalytic material that you're modifying via the solar thermal energy. So with that, I think I'll stop and turn it over to the next folks.
All right, thanks, Avi. All right, let's go to the next slide. I think we'll keep on the theme of hybrid systems that have potential to utilize both electricity, heat. We'll turn it over to our former colleague who's been highlighted quite a bit today, Jason Marcinkowski, who knows really well the hydrogen space and really opportunities to bring it to the nuclear office program. So thank you, Jason, for joining us, and we look forward to hearing from you.
Thanks, Eric. I manage Nuclear Energy's Integrated Energy Systems Program, as well as the Light Water Reactor Sustainability Program's Flexible Plant Operation and Generation Pathway. Both of these areas are under the Office of Reactor Fleet and Advanced Reactor Deployment, led by Alice Capinini. As Jesse said, I recently moved to the nuclear offices from the hydrogen program, where I was responsible for both high temperature electrolysis testing and the use of electrolyzers to balance the grid, as well as developing the hydrogen truck targets. So, and more recently, the work in collaboration with nuclear and hydrogen. The nuclear office has been a great partner to the hydrogen program, and vice versa. Next slide, please. If you didn't see Allison Hahn's presentation earlier today, I recommend checking it out to see the benefits of current and future nuclear energy. I don't have time to cover that in this presentation. In integrated energy systems, we emphasize 3 areas: thermal energy storage to provide flexible capacity to the grid, integrating industrial and chemical plants, including hydrogen and also carbon utilization, and heat export, which can be expanded with the development of small scale or microreactors that can be co-located with more applications. As Allison mentioned, we've successfully selected 4 projects to integrate hydrogen production with nuclear plants. These projects really break down the technical barriers and address the regulatory process for integrating electrolysis with nuclear plants. Most of the hydrogen produced in these smaller scale demos will be for on-site use. However, the larger vision for nuclear hydrogen production is twofold. First, we want to expand the role of clean nuclear energy beyond the grid into the transportation and industrial sectors. Second, by reducing hydrogen production during peak demand on the grid, we can add grid scale flexibility to nuclear's clean firm capacity. This relies on hydrogen for what we call one-way energy storage. Next slide, please. Through DOE's Advanced Reactor Demonstration Program, we are on track to provide the next generation of clean nuclear energy by the end of this decade. Carbon-free electricity 24/7, 365 days a year. This is the Natrium sodium-cooled fast reactor, and it makes about 345 megawatts nominal clean electrical power. And it's the first nuclear power plant to incorporate a large-scale thermal energy storage system and flexes up to 500 megawatts for 5.5 hours, accommodate changes in the availability of solar and wind on the grid. Natrium's energy conversion technology leverages the existing molten salt technology from the concentrated solar power industry. It also uses combined cycle gas turbine technology typical in fossil plants. And last week, the governor of Wyoming and TerraPower announced siting Natrium at a retired coal plant to provide jobs and leverage existing energy infrastructure. While this integrated system focuses on thermal storage, hydrogen generation is also being considered with high temperature heat available for steam electrolysis. Next slide. These images show what the future of nuclear and hydrogen could look like if we produce hydrogen from nuclear microreactors. These notional specifications show how an on-site 60 megawatt microreactor could power a 12-position fueling station that could service over 500 hydrogen long-haul trucks per day. This is just one way we envision the nuclear future. In 2023, DOE plans to start operating MARVEL, a nuclear test platform for microreactors. And by the end of this year, Magnet, which is the non-nuclear microreactor emulator, will be integrated with the high-temperature steam electrolysis test facility and real-time grid simulator at the Idaho National Laboratory. In this example, we see how systems integration can eliminate the large cost of transporting hydrogen to a fueling station while realizing the full potential of clean, reliable nuclear energy. These are just 2 examples, this and the Natrium reactor, of many high-impact integrated energy systems that we're looking at today. We're working more closely than ever with our colleagues in other offices to advance U.S. energy systems with a holistic perspective on all of the technologies available to us. Thanks.
All right. Can we go to the next slide, please? All right, we'll round off our panelists with Bhima Sastry, who is in the Office of Fossil Energy, is a leader in the systems integration field. Bhima, could you take it away? And then we'll, at the end of that, we'll come back to some opportunities for broader collaboration discussion amongst all the offices.
Thank you, Eric. Really appreciate it. It's good to come on last too. So I'm Bhima Sastry. I'm the Director of Cross-Cutting R&D and Systems Integration in the Office of Fossil Energy and Carbon Management. I'd like to stay on this slide and just speak a little bit about what's been covered so far. I mean, the perspectives that have been provided by all the programs. There's one thing that stands out, I mean, we in the Office of Fossil Energy and Carbon Management, we have traditionally looked at, large-scale generation, which are remotely located from consumers, centralized control structures, minimal feedback, limited energy storage and passive loads. That's the kind of thing that was traditional. I think what we've heard today from all the program managers and who spoke about the programs that they're managing, it's very clear that the U.S. electric generation mix is changed dramatically. We have a lot of increased generation from highly flexible natural gas. We have rapid deployment of and penetration of variable renewable sources. Solar, we covered that, and wind by Jian. And there's decreased generation from traditional baseload resources. I mean, that's the what's happened over the last 1 decade. And the other changes that are in the works basically are what Eric mentioned right at the beginning, deployment of energy storage technologies and the greater use of digital and communication technologies in the control of power systems. So what all this means is that we need to start thinking of new ways of dispatchability, flexibility, and reliability that offer a potential for a more optimized, cost-effective modern energy sector from fuel generation to deliver this load. And the Office of Fossil Energy and Carbon Management is undertaking R&D projects to address challenges and promote innovations in integrated energy systems, something that Jason touched upon. Basically, our office goal is to deploy flexible capacity to the electric grid with low-cost thermal energy storage systems, produce transportation fuels such as hydrogen, ammonia, and heat from industrial applications, and expand the use of carbon-free energy. We're working with all the R&D projects to decarbonize the electric sector by 2035. And last but not least, we've been congressionally directed to work with all the offices that have kind of spoken so far to put together an integrated energy systems initiative. And we're working with DOE-wide Grid Modernization Initiative and the Energy Storage and Grant Challenge that has been come out, and trying to put together this congressionally directed report. If you go to the next slide, I just have one slide and basically shows the IES, that's the integration systems effort to enable new technologies. What the slide shows, is the 4.2 billion kilowatt hours coming from so many different sources, and obviously fossil fuels dominate that. There's a lot of them coming from nuclear too, which is a baseload type of operations, but others are coming along. And we need to be looking at ways to integrate all of this. And recent studies have highlighted opportunities for such integrated energy systems, which basically incorporate diverse energy sources that you see here, and in environmentally sustainable, cost-effective, and reliable way of generating power and delivering it to the consumers. So what we believe in, and what's shown on the right, the tightly coupled hybrid energy systems, basically is a system that enables more efficient utilization of multiple feedstocks, be it nuclear, fossil, any of those, and it creates services of increased coordination and direct hybridization, basically allowing dynamic optimization of the grid. which of supply and demand basically. And this is such a deployment and development of integrated energy systems we believe will enable the deep decarbonization of the US economy and revitalize industry and manufacturing as well. With that, I'll stop and we'll probably take some questions when the panel starts.
Right,
Eric?
thanks, Bhima. And if we can actually move to the next slide. Thanks. We'll have one overarching question. I think you, this panel and Bhima, you brought it back to the theme of the day that we started with from the Secretary Granholm all the way through to the presentations that we've heard, that the hydrogen shot is really offers new opportunities. We've all worked together quite well and across the DOE offices in many spaces, including hydrogen. But I think with this new incentive of the hydrogen shot, we'll be seeing each other even more. So I look forward to it. But I think, since we've got about 10 minutes left here, I want to pass the mic backwards. We'll start with you, Bhima, again on the question. Where do you see some of these major, certainly challenges, but really opportunities for collaboration across our offices in terms of supporting this hydrogen shot and the types of exciting research that we can do together? Let's start with you, Bhima.
Yeah, thanks. Yeah, I'll be brief. Our office is again, when we say hydrogen, the thing is, it's a storage medium. It's a medium for generating power. It's got a whole bunch of things that we do. We in our office are looking at hydrogen production on a large scale. The graphic that I showed about the kind of electricity that is needed for the country. You need to generate hydrogen, and traditionally, fossil fuels have been the biggest resource for generating hydrogen through SMR, and that's been the traditional way of getting hydrogen. But we are looking at new ways of producing hydrogen through gasification of biomass, plastics, coal waste, and talk about blue hydrogen, and there's also green hydrogen initiatives. And I think I believe that integrating that, and then the fact that we're looking at this integrated energy systems report and the work that we're working with other offices, NE and solar and other offices, clearly tells us that the path forward really is something where we're going to have a mix of all of this, and that hydrogen production is going to play a role. In our office, I believe has got a big thing to say, not just in hydrogen production, but also in terms of how we're going to use and clean out the fossil fuels by 2035.
Great, thanks, Bhima. Jason, do you want to take the mic? And you're on mute.
Sure, I'll be a little more specific in my response, I guess. I'm really excited about what Neha just mentioned in one of her analyses, drop-in synthetic fuels. We can leverage the hydrogen and heat produced from nuclear plants now that we have hydrogen produced from nuclear plants, or soon will be. And there are already processes that can work for making this in fuels. We can get CO2 from nearby ethanol plants or natural gas peaking plants, and even direct air capture systems. The big advantage here is that we can leverage technologies developed in the biomass and fossil energy programs, the massive fueling infrastructure that already exists today, and the massive vehicle fleet that already exists today, developed over the past century. This includes also technologies from the Vehicle Technologies Office, such as plug-in hybrids and hybrid vehicles that can more than double the fleet fuel economy. On top of that, the drop-in syn fuels would have at least net zero emissions. And if we consider a 20-year plus time frame to turn over the vehicle fleet, or deploy an alternate fueling or charging infrastructure, or to provide a clean electricity generation grid to power our electric cars, projects like this could significantly accelerate the path to decarbonization, providing net zero or zero carbon fuel into the existing infrastructure and vehicle fleet, all while we support the buildup of hydrogen production for the scale up of hydrogen stations and fuel cell vehicles over the next several decades. It will be challenging. We would be competing head to head with low cost oil, so we'd have a lot of work to do to reduce the cost of manufacturing, constructing these plants, and we'd have to learn how to operate them more efficiently and leverage the places where we can take the existing processes and inject nuclear heat into those to help make them cleaner and more efficient.
Great, thanks, Jason. Avi, I'll pass the mic to you.
Yeah, similar to Jason, I'm really excited by the opportunity that CSP has to deliver renewable heat to existing industrial processes. We know that, looking forward, the supply of non-emitting heat to existing thermal processes is one of the big challenges with decarbonization of the full energy sector. And we've all been talking about processes that are largely thermally driven. CSP has that potential now to deliver relatively high temperature heat, 400, 565 degrees C, and we're working on technologies to go even higher. I think that's particularly interesting as we look at hydrogen specifically because of the opportunity for processes like high temperature electrolysis of water to generate hydrogen, which has the potential of being significantly more efficient than conventional low temperature electrolysis, and therefore potentially lower cost hydrogen. And I'm really excited about the potential of CSP to couple, again, both to the thermal and the electrical parts of that process. So I think there's a lot of potential there, and I'm certainly looking forward to working with Eric and his team on that.
All right, thanks, Avi. Jan. And you're on mute, my favorite expression.
Thank you. In wind office, hydrogen can be produced by land-based wind, offshore wind, and distributed wind. As I said, offshore wind is well positioned now, and especially with recent DOE, DOI, and Department of Commerce announcement to expedite the offshore wind deployment. European is ahead of us in offshore wind and hydrogen demonstration. US, we are playing catch up, especially in the area of the design, control, and hardware development and demonstration of offshore wind and hydrogen. And also, we are also interested in hydrogen, not just for regenerating electricity, but also to produce renewable fuel for other industrial process, and maybe to generate through some kind of hydrogen renewable fuel turbine. So I think there are just a lot of opportunities, and even to collaborate with within DOE offices and to collaborate with industries as well.
Very good, thank you. And let's turn it to Paul.
Hi, Eric. So I think the big opportunity from the analytical space is really thinking about how hydrogen fits into this bigger picture, essentially as an energy medium that can, go directly to the power sector and be combusted, or be a fuel for various other things. And so I think, the big collaborative opportunity for DOE is really thinking about, how do we build these system level analytical frameworks and system level tools to, really truly understand kind of the feedbacks across the sectors that, that hydrogen can have. And how do we build them into kind of our larger system level analyses so that we can really kind of map out kind of the optimal pathway to get to these, these high levels of decarbonization, both by 2035 and 2050. So lots of work in the future to be done across all of DOE.
All right, thanks, Paul. Let's come back to Eric, who we kept awake, I think. But maybe you can get the last word on our panel, then we'll wrap it up. And yeah, thanks, Eric.
Sure, I'll echo Paul's comments about the system level analysis. I think one of the exciting things about hydrogen is the optionality that it will give the power system. As a high quality fuel that is relatively storable, very stable, and potentially has its own transportation network, you have the potential to really give system operators and planners new degrees of flexibility in how we operate and even plan and invest in the power grid itself. And so as as a medium that has its own independent values as well as value to the grid, I think there's really rich analyses there that I'm looking forward to pursuing, and certainly a lot of opportunity in the way it gives us pathways to very high levels of decarbonization on the grid. Thanks.
Good. Thanks, Eric. And I'd like
Eric,
to take this.
Eric,
Yeah,
if
go
I
ahead,
may,
Bhima.
this is Bhima. Just one thing I'd like to also mention is that, cutting across divisions, solar and nuclear, we're working with them to, EERE and NE basically on looking at new power cycles too. And I think one of them is a supercritical CO2 power cycle, which allows higher efficiencies of electricity generation. And I think those are areas that definitely will contribute towards what the integrated energy systems will look like in the future.
And that really
waste heat recovery and such. Yeah.
Yeah, brings up a really good point. We have to be looking at what can we do now. What is low hanging fruit to move this ball forward, but what does the future really hold? I think that's what's in our mind as well. Looking at these high temperature materials or high temperature systems, we've been thinking about this. I mean, what if someone really has those systems that can operate at 700 degrees? That's a game changer as well, right? In terms of efficiently producing hydrogen. So, this is why it's so important for all of us to be working together to understand these opportunities and to make them happen, both in the near-term opportunities as well as the longer-term ones. So I think that's kind of the theme of today. I think it really encapsulates how hydrogen really is an integrator and enabler for integrated and hybrid energy systems. I think hydrogen shot, or the hydrogen Earthshot, is exciting, and I think we'll be seeing a lot more of each other as the days move forward. And with that, I want to give my special thanks to the panelists here who really experts in their fields and spent time with us at our AMR. We really appreciate it. I don't know if there's any virtual clapping allowed, but I'm going to give you an actual clap. But thank you to that. The next item on our agenda will be also quite exciting. That'll be the award ceremony. And for that, I will be turning it over to Sunita and to Shauna to initiate that part of our program.